This lecture is on chapter 6.3 to 6.4 on stoichiometry and percent yield. So stoichiometry. We now know that balanced chemical equations provide the ratio of molecules or moles necessary for a reaction to occur. So moles and molecules are not very useful in everyday life. We typically make measurements using mass and volume. Okay, so like I said in the last lecture, you're not going to go into the laboratory and say, hey, Steve, give me 1 mole of sodium chloride. Okay, you're going to say, hey, give me 10 grams of sodium chloride. Okay, so we need to be able to easily convert between our number of moles and these more usable macroscopic scales in terms of mass, volume, etc. So stoichiometry is the chemical arithmetic needed to convert between number of moles, number of molecules, mass, and volume. And so to do that, we use a few different types of conversion factors. We have some of the conversion factors we readily see are the molar mass, density, and so on and so forth. Okay, so we're going to use these chemical equations that are balanced in order for us to guide our stoichiometry conversions between our different units. Okay, so let's look at the general form of a stoichiometry problem. So consider a chemical equation with the following form. So we have A plus B yields C plus D. So, okay, so this is, we have A and B sort of taking the place of of our reactants, and C and D taking place of our products. And then we have the lowercase a and B are identifying our stoichiometric coefficients. Okay, so that's the molar ratio between each of our constituent elements. So the stoichiometry allows for the conversion between mass of one molecule and the amount, either in mass or moles, of any other molecule, whether it's a reactant or a product. So for any of these problems, you can write a flow chart of the types of conversions that we go to. So if we start off with a number of grams of A, and we end up wanting to convert to number of grams of B, we cannot directly convert between the mass of one molecule to the mass of another molecule. We have to first convert to number of moles. The only way you can convert between an amount of one substance and another is by converting to moles. Okay, that is very, very important. I'm going to say that again. The only way that you can convert from the amount of one substance to the amount of another substance is by first converting to moles. Okay, and so the more and more you practice this, the more this is going to become second nature. So if we want to go from grams of A to grams of B, we know we can't directly convert. We need to first convert to moles. So first we would take grams of A into moles of A, and then we can convert moles of A into moles of B, and then we can convert moles of B back to grams of B. Okay, and the same sort of idea here would be if we wanted to convert from grams of A to grams of C or grams of A to grams of D. The same sort of thing works for each different type of conversion. And so once we have this flow chart here of the identity of each that we have to convert to, we can identify each of these arrows here are going to be a different conversion factor that we have to identify. So to convert from grams of A to moles of A, we need the molar mass of A. To convert between moles of A to moles of B, we need the molar ratio between A and B, which are simply your stoichiometric coefficients. And then to convert back from moles of B to grams of B, we again need the molar mass of B. Okay, so hopefully if you're confused at all, this will become much more clear in our upcoming examples. Okay, so in order for us to convert easily between our mass and number of moles, we need to take a look at our molar mass or our molecular weight or our formula weight. So the molecular weight is defined as the sum of the atomic weights of all atoms in a molecule, whereas the formula weight is the sum of the atomic weights of all atoms in a formula unit of any compound, molecular or ionic. Okay, so the difference between these two terms here is molecular weight technically only talks about molecules. So those are individual molecules held together by covalent bonds. Whereas formula weight is talking about the atomic weight of either a covalently bound molecule or an ionic compound. Okay, so we know if we have sodium and chloride forming together to form the sodium chloride crystal lattice, we don't exactly know what the quote molecular weight is because it depends on the how many repeating units of sodium chloride composes the larger crystal lattice. Whereas if you're talking about carbon dioxide, you know that every carbon monoxide or carbon dioxide molecule consists of one carbon and two oxygens. So what the formula weight is talking about is if you're talking about an ionic compound, such as sodium chloride, you simply just add up the atomic weights of the constituent ions for that ionic compound. So you would look up the atomic weight for sodium, and then you add it to the atomic weight of chlorine. Okay, so it's simply a semantic sort of thing between molecular weight and formula weight. It's just important for you to know the difference between the two. But really, in general application, these terms are generally interchangeable. Okay, so I asked you all to take a moment here to determine the formula weight for all three molecules in the following reaction. So pause the video and take a moment to work through that. Okay, so first we're going to take a look at C2H4. All right, so we know that this molecule here is composed of two carbon atoms and four hydrogen atoms. So if we're determining the formula weight of the C2H4, what we need to do is add together the formula weight or the atomic weights for the carbons plus the atomic weight for the hydrogens. So if we take a look on the periodic table, we see the atomic weight for carbon is 12.0111. And then since we have two, we're going to multiply that amount by two. And then we're going to add it by our atomic weight for hydrogen, which on our periodic table is 1.0079. And since we have four hydrogen atoms, we're going to multiply that value by 4. And so our overall formula weight for C2H4 is going to be equal to 28.0538. Okay, and so the units for this are going to depend on whether we're actually talking about the molar mass or the formula weight of the specific molecule. So if we're talking about specific molecule, this will be in AMU per molecule, or we can have it in formula weight as grams per mole. So remember that those terms are the numerical value here is interchangeable. The only thing you change between the molar weight and the formula weight is just the final unit at the end. Okay, next, if we're dealing with HCl, we have one hydrogen and one chlorine. So we simply add together 1.0079 for hydrogen plus 35.453 for our chlorine. And so these values come together to equal 36.4609. And again, that'll be AMU per molecule or gram per mole, depending on which unit that you're interested in. Okay, and finally, for the C2H5Cl, we are going to have the atomic weight for carbon, which is 12.0111 times 2, plus the formula weight for hydrogen, 1.0079 times 5, plus the formula weight for chlorine, which is going to be 35.453. And that's going to come together to equal 65.5147 mu per molecule or gram per mole. Okay? So, as I stated before with this discussion here, we can either express these formula weights in the atomic weight or molar mass. All we have to do is just swap out the specific units. Okay, and then once we have this molar mass, so the molar mass has units of grams over moles. This can now be used as a conversion factor for you to be able to convert between number of grams and number of moles. So you can either go in one direction to convert from grams to moles, or you can go in the other direction using the conversion factor to go from number of moles to number of grams. And so we're going to work through examples of each of those. And it's important to know we also have a conversion factor stating that 1 mole is equal to 6.022 times 10 to the 23rd molecules. So you can't forget that secondary definition of a mole. All right, so let's work through a few problems here. So first, let's take a look at a mass to mole conversion. So how many moles of ethylene gas, which is the C2H4, are in 15 grams? Okay, so as with any problem, we're going to start off with our measured value over 1. So we have 15.0 grams of C2H4 over 1. And then we know we want to convert this value. So again, it's a good idea to sort of write a flow chart of what we're trying to do. We're trying to go from the mass of C2H4 to the number of moles of C2H4. Okay, and so it's a simple one-step conversion here. And we identify for each arrow what conversion factor we're going to use. And to go from mass to moles, we need the molar mass, which we abbreviate MM for the C2H4. Okay, so we already calculated that the molar mass from C2H4 is 28.0538 from that last problem we worked through. So now we just need to determine how do we represent this molar mass in the actual problem. So we know the units of molar mass are in grams per mole. So we need to be able to convert our mass in grams to a final answer that's going to be in number of moles. And so that means we need to finish the problem with the unit of moles in the numerator. And in order to cancel out this grams that we start off with in the numerator, the only way to cancel that out is by having grams present again in the denominator. Grams of C2H2, or C2H4, excuse me. And if we want to end with moles, we can see that we need to have moles of C2H4 in the top. And so that way we're going to have grams cancel and we're going to end up with moles. And so the way that we're going to represent this conversion factor is by having our 28.0538 grams of C2H4 per 1 mole of C2H4. Again, we're going to have canceling out, and then we can now plug and chug to get our final answer of 0.535 moles of C2H4. Okay, a pretty simple, straightforward conversion. Next, we're going to convert between moles and mass. So doing the opposite direction conversion that we just did in the last problem. So I ask you, how many grams of HCl are in 0.536 moles? Okay, to work through this, again, we take our measured value over 1, as always, 0.536 moles of HCl. Okay, and so again, we want to write out our flow chart of how we're going to solve this problem. So we're starting out in moles of HCl. And we want to convert this into the mass of HCl. So it's a simple one-step process. And we identify our conversion factor between moles and mass. Again, is going to be our molar mass, and this time of HCl. So we need to identify how do we set up this conversion factor in order to find our final units, which are going to be in grams. So we know that we need to leave grams on our final numerator, and we need to cancel out this number of moles. So in order to do that, we write the molar mass, 36.4609 grams of HCl. Again, this number we determined in a previous problem. that 36.4609 grams of HCl per 1 mole of HCl. So therefore, this mole of HCl can cancel, and we finish with grams of HCl on the top. Plug and chug, we get a final answer of 19.5 grams of HCl. So a very simple one-step conversion. All right, so let's move on to a little more complex of a problem. So aqueous solutions of sodium hypochlorite, which is NaOCl, best known as household bleach, are prepared by the reaction of sodium hydroxide with chlorine gas. And we have the chemical equation provided down here below. How many grams of NaOH are needed to react with 25.0 grams of Cl2 gas? Okay, so to work through this problem, it's a good idea for us to start off with writing our flow chart. So we know that we started off with a mass of Cl2, and we know that we want to we want to end the problem with mass of NaOH. So we know that we cannot directly convert between the mass of one compound to the mass of another compound. We're not able to do that. The only way to convert between the amount of one substance and the amount of the other is to first convert to number of moles. So we need to first take the mass of Cl2 into number of moles of Cl2. Then we can convert from number of moles of Cl2 to moles of NaOH. And then we can convert from moles of NaOH to mass of NaOH. So now it's just a matter of identifying the proper conversion factors for each of these different specific conversions. And so we know between mass and moles, we're going to be dealing with the molar mass of Cl2. Between moles and mass of NaOH, we're going to be talking about the molar mass of NaOH. So the same problems we just worked through. And then between moles and moles, this is going to be the molar ratio. Okay, and we find this molar ratio from the chemical equation. Okay, so if we take a look at our chemical equation here, we have 2 NaOH aqueous plus Cl2 gas is going to yield NaOCl aqueous plus NaCl, which is aqueous, plus H2O, which is liquid. So whenever you deal with a chemical equation, you need to make sure that it is balanced before you use it. Okay, you cannot assume that a chemical equation that's been given to you has been balanced. So let's go through and make sure that we're actually dealing with a balanced equation. So we have sodium. How many sodiums we have? 2 times 1, so we have 2 sodiums here. Oxygen, we have 2 times 1 is 2 oxygens. Hydrogen, we have 2 times 1 is 2 hydrogens. And chlorine, we have 2. So we have 2 of everything. Sodium, we have 1 sodium here, 1 sodium there, that gives us 2. Oxygen, we have 1 oxygen here, 1 oxygen there, gives us 2. Hydrogen, the only 2 hydrogens are in water, so we have there. And then chlorine, 1 chlorine here, 1 chlorine there, gives us 2. So yes, we are dealing with a balanced equation. So we are free to move forward. Okay, so the next step. So we have this balanced equation. So I'm going to erase this balanced equation, but know that you can look back at your slide here and see that the equation that's provided to you is indeed balanced. Okay, so we can take a look at that equation now, and we can determine our molar ratio from that equation. And so if we're converting between Cl2, so actually I'm going to write that equation back up here on the board just to illustrate the molar ratio. Okay, so our molar ratio between Cl2, so we look at our stoichiometric coefficient here, which is a 1, and NaOH, which is going to be our stoichiometric coefficient here of 2. So that's going to be a 1 to 2 molar ratio. Again, stoichiometric coefficients give us the molar ratio 1 mole of Cl2 gives us 2 moles of NaOH. Okay, again, we determine that molar ratio looking at our chemical equation. Okay, so if you need to refer to that equation, look back at your slide. So the next step, we need to determine our conversion factors, these molar masses of Cl2 and NaOH. And so to do that, we need to calculate the molar mass. So the molar mass of Cl2 is going to equal, again, we're going to look at our periodic table and see that chlorine has an atomic weight of 35.453 times 2 atoms is going to give us an answer of 70.906. And so here we need molar mass, so we're looking for grams per mole units. Okay, so we can write that up here, 70.906 grams per mole. Now our molar mass of our NaOH, we're going to see the molar mass for sodium is going to be equal to 22.9898. And there's only 1 sodium in NaOH, so we can multiply that by 1. Plus our oxygen, which is 15.9994. Again, we're finding these from the periodic table. There's only 1 oxygen, so we multiply that by 1. Plus the molar mass of hydrogen, which on the periodic table shows 1.0079, again, times 1 because there's only 1 hydrogen atom in NaOH. Plug and chug, put all these guys together, and you're going to get a molar mass of 39.997, again, grams per mole. So we can write that up here, 39.997 grams per mole. Okay, so once we've done all of this upfront work and identified the values for each of these conversion factors, now solving this problem becomes quite routine. So we go back to the problem here and we take a look at the measured value that's given to us. So our measured value is going to be 25.0 grams of Cl2. Always take our measured value over 1. We're going to convert from mass Cl2 to moles of Cl2. So we know that grams of Cl2 has to be on the bottom to cancel. So we have our value here, 70.906 grams of Cl2 per 1 mole of Cl2. Now we need to convert from moles of Cl2 to moles of NaOH. So we have our conversion factor, which is 1 to 2. So for every 1 mole of Cl2, you have 2 moles of NaOH. Again, that conversion factor is the molar ratio coming from our chemical equation. So now we have moles of NaOH that we have to convert to grams. So we're going to again use our conversion factor, the molar mass of NaOH. The number of moles has to be on the bottom to cancel, and that leaves us grams on the top for our final answer. So we can say that for every 1 mole of NaOH, there is 39.997 grams of NaOH. And so we can see here, grams of Cl cancel, moles of Cl cancel, moles of NaOH cancel, and then we're left with grams of NaOH. And so our final answer after we plug and chug gives us 28.2 grams of NaOH. And so here we're going to, we need to keep in mind our significant figures. We can see our starting value that's given to us has 3 significant figures, and we've all done multiplication and division here. So our final answer needs to be cut to a final answer of 3 sig figs. Okay, so really, if you work through and write this flow chart to start out a problem, you can hopefully see that these stoichiometry problems, it's really not math, it's only just simple conversions. All right, so let's take a look at another problem using stoichiometry. And so this is another mass-to-mass conversion. And so for this problem, I invite you to work through, pause the video and work through on your own before logging back in. Okay, so the combustion of hydrocarbons releases carbon dioxide into the atmosphere. Some chemical reactions can remove or sequester carbon dioxide from the atmosphere into a pool for long-term storage. Below is a sequester reaction where carbon dioxide combines with a naturally occurring mineral. So what is the mass in kilograms of magnesium silicate, which is the Mg2SiO4, needed to sequester 1 petrogram, which it gives us our conversion factor. The petrogram is 10 to the 15 grams of carbon dioxide. Okay, so this seems like a very scary problem here, but really you're going to see that it's exactly the same as the last problem. It just involves a couple unit conversions. Okay, so let's take a look to see what we have to do. So again, we're going to start off with our flow chart. We start off with a mass of CO2. We need to convert that, and so our final answer needs to be in mass of our Mg2SiO4. And we know that we cannot directly convert from the mass of one substance to the mass of the other. We first need to convert to number of moles. So our mass of CO2, we're going to take to moles of CO2, and then convert from moles of CO2 to moles of the Mg2SiO4. And then from there, we can convert to the mass of Mg2SiO4. And so identifying our proper conversion factors to go between mass and moles, we're going to be looking for the molar mass of CO2. To go between moles to mass, we're going to be looking for the molar mass of Mg2SiO4. And between number of moles of CO2 and moles of Mg2SiO4, we're going to be looking for the molar ratio. So again, that's going to be coming from our chemical equation. So next we want to take a look at our chemical equation, our Mg2SiO4 solid plus 2 CO2 yielding 2 MgCO3 solid plus SiO2. And so we need to make sure that this chemical equation that's provided to us is balanced. So we'll go through and identify each atom. So magnesium, we have 2. Silicon, we have 1. Oxygen, we have 4 plus 2 times 2 is 4. So we have 8 total oxygens. Carbon, we have 2 times 1 is 2. Looking over at the products, we have 2 magnesiums. 2 times 1 carbon gives us 2. 2 times 3 oxygens gives us 6, plus another 2 gives us 8. And then silicon, we have 1. So we can see that this overall chemical equation is balanced. And so we can look at this chemical equation and we can find our molar ratio. So our molar ratio between CO2 and Mg2SiO4, so CO2 and Mg2SiO4, we have a 2 to 1, so there's a 1 and a 2, 2 to 1 molar ratio. Okay, next, to determine these conversion factors, we're going to need to find the molecular weight of each one. So for the molecular weight of CO2, okay, so that's going to be our atomic weight of carbon, which is 12.0111 grams per mole times 1. So actually, to save space, I'm going to cut those units out right here. Okay, that's for the carbon. And then plus our atomic weight for oxygen. Again, these values coming from the periodic table, 15.9994 times 2. Plug and chug here, we get a value of 44.0099 grams per mole of CO2. So we can write that up here as our conversion factor here, 44.0099 grams per mole. Okay, next we find our molar mass for the Mg2SiO4. So that's going to be our atomic weight for magnesium, 24.305 times 2, because there's 2, plus the atomic weight for silicon, which is 28.086 times 1, because there's only one silicon, plus our atomic weight for oxygen, which is 15.9994 times 4, because there's 4 oxygens. So if we plug and chug here, we get a final answer of 140.6936 grams per mole for the Mg2SiO4. So we can write that up here on the top. 140.6936 grams per mole. And so you can see we're keeping lots of decimal places for our molar masses. The reason for that is because we don't want our calculations down the road to be altered by any rounding errors associated with our constants. So you want to keep as many decimal places as you can. Okay, so next we want to do our conversion. All right, so we start off now with our measured value over 1, which is going to be 1 petrogram, so 1 pg, okay, and that's 1 pg of, what's the value we're starting with? CO2. Sorry about that. And then so we need to now convert this from pg, petrograms, into grams, because we can see our conversion factor here is in the grams per mole. So here we take a look at our dimensional analysis. We can see that 1 petrogram of CO2 would be equal to 1 times 10 to the 15 grams of CO2. So it's a simple conversion factor to take it from this kind of intimidating petrogram into a very usable grams. All right, so now we can go from our mass of CO2 to number of moles of CO2 using our molar mass, and we want to cancel grams, so the grams has to be on the bottom, 44.0099 grams of CO2 per mole of CO2. Now we use our molar ratio to convert between moles of CO2 and moles of Mg2SiO4. And so moles of CO2 has to go on the bottom, and we can see 2-to-1 ratio. So for every 2 moles of CO2, you have 1 mole of the Mg2SiO4. Excuse me. Okay, so now we convert between moles of Mg2SiO4 to mass in grams. So we're going to jump down here. So we know we need to have moles of Mg2SiO4 on the bottom to cancel out. So we're going to have our molar mass. So we're going to have, for every 1 mole of Mg2SiO4, our molar mass says 140.6936 grams of Mg2SiO4. Okay, and so our final answer asks for our final unit to be in kilograms instead of grams. So our final step is to convert between kilograms and grams. And so we know that 1 kilogram of Mg2SiO4 is going to be equal to 1 times 10 to the 3 grams of Mg2SiO4. There's 1,000 grams per kilogram. All right, so we can see the petrograms cancel, the grams cancel, the moles cancel, the moles cancel, the grams cancel, and we have a final answer in kilograms. Okay, so if we plug and chug this answer, we get a final answer. So I kind of ran out of board space, so we'll write it right up here. Our final answer is going to be 1.60 times 10 to the 12 kilograms of Mg2SiO4. So we think that might be the final answer, but it's not. If we take a look at our starting value that was given to us, we only have one significant figure. So what we need to report our final answer in is in one significant figure. So therefore, we need to round up to one final answer. So our final answer here is 2 times 10 to the 12 kilograms of Mg2SiO4. Okay, so that is our final answer given to us with the proper number of significant figures. 2 times 10 to the 12 kilograms of Mg2SiO4. Okay, so now that we've worked through stoichiometry problems and stoichiometry problems that also incorporate changes in specific units, now we can discuss the yield of chemical reactions. So rarely do 100% of the reactants actually convert over to form products. There can be side reactions, there can be loss of sample due to experimental mishaps, there could be lots of different reasons that a yield doesn't complete to its full fruition. And so we need to be able to account for that loss of our expected sample throughout an actual synthesis reaction. So we have a couple terms that explain this expected amount versus the amount that we actually observe. And so the first term is called experimental yield. So the experimental yield is the amount of product actually formed in a reaction. And so this term makes sense because experimental, this is what you actually form when you're performing what you observe after performing the experiment. The second term is called theoretical yield, which is the amount of product that's theoretically possible to be formed. So this is the amount, the theoretical yield is the amount that you can produce based on your calculation. So the amounts that we just determined up on the board in the last 4 problems, these are all theoretical yields. Whereas the experimental yield, that would be the amount that of the product that you actually measure at the end of a reaction. All right, so theoretical, that's based on theory, mathematics. Experimental is based on actual production, and this is an observed value, either mass or volume. And so we have a third term here, which determines the percent efficiency of a chemical reaction, and it's called the percent yield. And so the percent yield is equal to the experimental yield over the theoretical yield times 100%. Okay, so this times 100%, it just turns that quantity into a percentage value that you can report. And so if you have a percent yield of 100%, that means that the experimental yield over theoretical yield is equal to 1, which means that those amounts are exactly the same. If you have a percent yield of 50%, that means that this experimental yield is half that of the theoretical yield. And so that would be a pretty poor return. And so you can actually get percent yields that are over 100%. So if you're producing a final product that may have a contamination in it, if you expect, say, 1 gram of product based on your theoretical yield, you can observe 1.2 grams if you have contaminants in your final product. And so that would be a percent yield over 100%. Okay, so those values are whether it's above 100% or below, those percent yields are all valid. So let's work through an example of a percent yield problem on the board together. So ethyl alcohol is prepared industrially by the reaction of ethylene, which is C2H4, with water. What is the percent yield of the reaction if 4.6 grams of ethylene produces 4.7 grams of ethyl alcohol? Okay, so we know that we're going to be talking about a percent yield problem. And so we know that our percent yield is going to equal the experimental over the theoretical times 100%. Okay, and so let's take a look at the problem and see which values are actually given to us. Okay, so if we go back through the problem, ethyl alcohol is prepared, so it sort of introduces the problem. So what is the percent yield of a reaction if 4.6 grams of ethylene produces 4.7 grams of ethyl alcohol? So we know that the experimental, the amount that's actually produced, is going to be this 4.7 grams that we actually have. Oh, so one more note that I want to pass on about percent yield. These experimental or theoretical values here can either be in moles or can be in mass. It doesn't matter. You can solve the problem in either way. The only thing is, each of the top and the bottom have to be the same. So either the experimental or theoretical both have to be in moles, or experimental and theoretical both have to be in mass. You can't mix the two. Okay, so we can just solve this one with mass over mass. So we know the experimental is going to be 4.7, but we don't have the theoretical amount of ethyl alcohol that we expect to have. We have 4.6 grams of the ethylene, which is the starting material, but we don't have the amount of ethyl alcohol that we expect to form. So therefore, we need to first solve for this theoretical value in order for us to solve the problem. And so for us to solve for that theoretical value, we simply need to do a stoichiometric conversion just like we've done previously. So if we write out our flowchart of what we need to do, we have a mass of ethylene. We need to end up with a mass of the ethyl alcohol, which is our C2H6O. Excuse me. We know we cannot convert straight from the mass of one material into mass of another. We need to first convert to moles. So we need to go to moles of ethylene. So ethylene, again, is going to be our C2H4. Now we can go from moles of ethylene to our moles of the C2H6O. And then we can convert to the mass of our ethyl alcohol, C2H6O. And so identifying our conversion factors, again, our mass to moles is going to be our molar mass of C2H4. Our conversion factor between moles to mass here are going to be the molar mass of the C2H6O. And our mole to mole conversion is going to be our molar ratio, which we take from our chemical equation. All right, the exact same problem that we had, same sort of problems we had previously. So let's take a look at our chemical equation and make sure that we're balanced. So we have C2H4 gas plus H2O liquid yields C2H6O liquid. So if we take a look, carbon, we have 2. Hydrogen, we have 4 plus 2 is 6. Oxygen, we have 1. Looking over here, carbon, we have 2. Hydrogen, we have 6. Oxygen, we have 1. So we are totally balanced here in our equation. So now determining our molar ratio between moles of ethylene and moles of ethyl alcohol, we're in a 1-to-1 ratio. Okay, so next we need to determine what are our molar masses of C2H4 and our molar masses of our ethyl alcohol. And so I'm going to save you guys the time of working through that. If you have questions how to work through molar mass, go back in the video and rewatch. So the molar mass for the C2H4 is going to be 28.05396 grams per mole. And the molar mass for ethyl alcohol is going to be 46.06924 grams per mole. Okay, so now we can work through our theoretical yield problem. So we start with our measured value, which is 4.6 grams of C2H4, measured value over 1 as always. We're going to convert from mass of ethylene to moles of ethylene using the molar mass, 28.05396 grams of C2H4 per mole. Convert between moles using our molar ratio. So 1 mole of C2H4 gives us 1 mole of the C2H6O. And then we convert from moles of ethyl alcohol to our mass of ethyl alcohol using our molar mass. So for every 1 mole of C2H6O, we have 46.06924 grams of C2H6O. And we can see all of our units are canceling, grams, moles, moles, leaving us with grams of product. And that grams of product comes out to 7.6 grams of C2H6O. And so this value here is our theoretical yield. So we can take this value and we can implant it now in our top equation. So if we take a look now, plug and chug our final equation, we can say that percent yield is equal to our experimental yield, which was given to us in the problem, 4.7 grams, over a theoretical yield, which we just solved as 7.6 grams. And again, these are both of C2H6O, C2H6O. You can see they're both the same units and both the same compound. Take that value times 100%, and we get a final answer of 62% efficiency. And if we take a look at our significant figures here, we can see we have two significant figures here, and our measured values that we had associated with the problem are also 2 sig figs. So our final answer should be in 2 sig figs. Okay, so there is a combustion stoichiometry worksheet that I'd like you all to work through to practice working through these stoichiometry problems. So the only way to get better at these problems is just to practice, practice, practice. Okay, so get at it and let me know if you have any questions. All right, that's it for the day. Thank you.